Good evening, everybody. I think we can start. Yeah, dear Professor Kaiser, dear colleagues Matthias Richter, Stephan Reitzenstein und Arne Schirrmacher, dear presidents of the American Physical Society, of the European Physical Society, and of the many national physical societies from Europe who are all here, dear guests on site here in the Magnus-Haus and also in the live stream, dear audience in the live stream. Yeah, it's the second part, a very warm welcome back to the second part of the opening of the quantum year here in Germany. I think we switch gears. You see, we now go on in English on the one hand, and with a second keynote lecture by David Kaiser from MIT, who will rather address, I think, the history also of quantum mechanics and how all of that has developed over during the last 100 years. I don't think there's a more suitable place in Berlin for such a topic on the history of physical science than the Magnus-Haus where we are here. So Gustav Magnus had run a physics lab here, and the building is hence also regarded as the oldest physics institute in Germany. And in 1845, I think precisely the very date, the 14th of January, the Physical Society, first of Berlin, emerged from the circle of participants in the physics colloquium established by Gustav Magnus. But many other famous physicists have come and gone here into this building. Among them Lagrange, Clausius, Gibbs, Helmholtz, Kirchhoff, Siemens, Tyndall, Wiedemann, to name just a few. You see, all the big names have been here 100 years ago or so. Well, I would like to be very brief now and therefore like directly to hand over to my colleague, Matthias Richter. He's the president of the Physikalische Gesellschaft zu Berlin. So that's the Berlin Physical Society. And well, I will wish all of us a very exciting evening. And please, Matthias.
Thank you very much. Yes, also a warm welcome from my side, from PGzB. This is in the program written. It's just the Berlin Physical Society. And we are the regional association for Berlin and Brandenburg. And we feel a little bit like a daughter of the German Physical Society. But it was our society, in fact, that was founded here in this building exactly 180 years ago. You mentioned that, which emerged from the physics colloquium that Heinrich Gustav Magnus organized here in this house. And it was until half a century later, in 1899, that the Berlin Physical Society was transformed into the German Physical Society. Daughter, and we feel a little bit like a mother for this reason. Yes, daughter and mother, two states at the same time. At least since the formulation of quantum theory 100 years ago, we have known that this is indeed possible. However, the year 1899 was not only of great importance for physical societies, but also for quantum physics. Otto Lummer and Ernst Pringsheim reported on measurements of black body radiation at the Physikalisch-Technische Reichsanstalt in Berlin-Charlottenburg. Their experimental results deviated from the radiation law of Willy Wien, and this led Max Planck, professor for theoretical physics at that time here in Berlin, to formulate his own radiation law 1 year later in 1900, which perfectly reproduced the measurements. What was new compared to Wien's radiation law, as we all know? was the assumption that the amount of energy in the emission and absorption of light is quantized. In this respect, we are celebrating 2 anniversaries of quantum physics this year. 125 years of discovery and 100 years of formulation. 2 anniversaries at the same time. It is also possible. Planck's radiation law was therefore the starting point for the development of quantum theory over the following 25 years. I think we will hear something of this. However, Planck's radiation law was also the starting point for the development of modern radiometry and thermometry. To this day, it is used to trace radiometric quantities back to temperature and vice versa, in particular at the Physikalisch-Technische Reichsanstalt, today's Berlin Institute of PGB, Germany's National Metrology Institute. 1 radiation law, 2 important consequences. What am I trying to say with all this? Both quantum theory and metrology teach us the principle of uncertainty. But are not uncertainty and ambiguity general characteristics of nature and life? A little less black or white, yes or no, true or false, good or bad, 0 or 1. Couldn't a little more diversity of thought make the world a little friendlier? Quantum theory, its 100 years and its principle of uncertainty, perhaps 2 reasons for commemoration, appreciation, and celebration. Thank you very much.
Dear presidents, dear invited guests, ladies and gentlemen, I would also like to, it's my great pleasure to warmly welcome you all also here in the Magnus-Haus for the second part of this official opening of the Quantum Year 2025. Yeah, hosting such an event in such a historic and distinguished venue is both an honor and also a very fitting choice, I would say, for the reasons you learned already. In fact, this Magnus-Haus, it stands for, as a symbol of scientific tradition and collaboration, and it makes it an ideal place to start a series of quantum events organized by the German Physical Society and our esteemed partners in Europe and worldwide. As many of you know, and as you've learned in the previous speeches, this Magnus-Haus has a long-standing tradition of bringing together scientists and to discuss the latest advancements in their fields, as we do today, I believe. And you all already know as well, it's named after Gustav Magnus, and he was the person who initiated all these colloquia, which are still going on here. And the first colloquium took place already in 1843, so more than 180 years ago. And since then, it has been a scientific hub, or has served as a hub for scientific exchange over more than 180 years already. So very historic and traditional. This place here has also welcomed, of course, very famous scientists like Albert Einstein and Planck 100 years ago. And I'm pretty sure they discussed lively about the newest results in quantum physics, atomic physics in that time. And this helped to form also this quantum theory, which we are celebrating today. Yeah, so again, it's a good idea to be here. In fact, the legacy of these famous scientists is fostering dialogue and innovation ever since then. And also today, quantum physics especially, and also, of course, quantum technology are central themes of the scientific program in our house. Yeah, just to give you one example, the future president of the German Physical Society, Dr. Heike Riel, who is here, of course, she gave about 2 years ago a very nice, very fascinating talk about the developments in quantum computing, which was very well received. And this is just one example of our program, which is dealing with quantum physics, quantum technology many times. Also looking ahead, we are thrilled to host, for instance, Professor Harald Weinfurter next Thursday also in the series of these events. And Harald Weinfurter, he is an expert in quantum communication, has delivered seminal results in this field, will give a talk on the latest results and developments in quantum communication. So if you are invited to come here again. Yeah, all of these events underscore the continued relevance of the Magnus-Haus as a venue for scientific dialogue, and I hope it will be like this also in the future. Again, I think it's a very fitting place to launch the Quantum Year 2025 here in this remarkable setting in the Magnus-Haus. And yeah, as we begin now with the second part of our evenings program, I wish you all an inspiring and enjoyable evening filled with engaged discussions and new insights. And I would like to extend especially my gratitude to Professor David Kaiser, who is here, for joining us tonight and for giving the lecture on this development of quantum theory, certainly one of the highlights of today's program. With this, I would like to thank you again for being here. And once again, welcome to the Magnus-Haus. Enjoy.
Yes, a warm welcome also from the side of the historians of physics. I'm Arne Schirrmacher from the History of Science group of the Humboldt University to Berlin. And today I'm representing the History of Physics division of the German Physical Society. And for some years now, we have organized a series of historical talks, which have become kind of a tradition already on the founding day of the Physikalische Gesellschaft, which, as has been mentioned several times, now turns 180. We've always tried to present the history of physics in a way that speaks to our interests today, as well as possibly provide some background for the future as well. When I suggested around 2 years ago that for the 2025 event we should ask the very speaker we have tonight, I couldn't foresee that this little, say, history of physics talks series on the foundation day would grow in such a big event tonight as a kick-off of the International Quantum Year in Germany. In the organization, so everything has changed. We had a double feature and we had much more people interested in the subject. We had to organize streaming. So one thing did not change overall, that was the name of tonight's speaker. Who else could address both physicists and people interested in the history of quantum physics as well as David Kaiser? In a way, we might also celebrate tonight David's annus mirabilis of 25 years ago. Since after studying physics at Dartmouth College and then proceeding to Harvard in the 1990s, it was in the year 2000 that he not only had completed 2 PhD theses, one is called with the name Making Theory, Producing Physics and Physicists in Post-War America. That's the historical one. And the other was Post-Inflation Reheating in an Expanding Universe. That's clearly physics. But he did not only complete 2 theses, he also became in the same year both a lecturer in physics and an associate professor in history of science at MIT. This double occupation eventually developed a Germeshausen professor in the history of science in 2011 and a professor in the Department of Physics in 2015, both at MIT. So I refrain from all these jokes, which probably invite themselves about complementarity of fields or probably also Kaiser's cat, but just say there's no wonder that for this annus mirabilis, given that he was awarded quite a number of teaching and publication prizes, and I just quote 3 from the history of physics field: a Kaiser Award for his book Drawing Theories Apart, the Dispersion of Feynman Diagrams in Post-War Physics, the History of Science Society Davis Prize for his very nice How the Hippies Saved Physics, Science, Counterculture and Quantum Revival. And Physics World recognized his book, Quantum Legacies, Dispatches from an Uncertain World, as best of physics in books of 2020. The APS had made him a fellow already in 2010. In parallel to all this, he worked on particle cosmology and participated in the cosmic Bell experiment, a test of quantum entanglement, and this collaborating here with Anton Zeilinger, among others. So please join me in welcoming David Kaiser to tell us more about the 20th century quantum legacies.
Great, thank you. Thank you very much. I want to thank both Presidents Richter, that's very easy to remember, the same name. Thank you both. And especially I want to thank my dear colleague, Arne Schirrmacher, Arne, for helping to arrange this invitation in the first place. And as you might expect, helping with so many details and arrangements all along the way. So Arne, really, thank you very much. It's been a wonderful visit. I'm very delighted to help the Deutsche Physikalische Gesellschaft and many other colleagues in the room launch this very exciting program to mark this quite remarkable occasion, the 100th anniversary of the formulation of something that many of us use every single day, the theory of quantum mechanics. Let's see. Okay. So especially after this really wonderful session that we got to enjoy just earlier this afternoon with Professor Ketterle and our other colleagues, I don't have to linger very long on some of the deep, I often call them delicious, beguiling, remarkably accurate, and yet also fundamentally strange features that still lurk at the core of quantum theory. Here's a short list. I'm sure all of us in the room can extend the list many times over, from quantum tunneling to superposition, entanglement, and of course beyond. What I want to do this evening is just at least begin a discussion about how these strange features and others were articulated, were fiercely debated, were eventually came under quite impressive testing during a rather strange century. So everything about this, it turns out, was strange, and I think also instructive, at least for the historian. From some, again, rather obvious events, the rise of fascism, the dawn of the nuclear age, a long simmering Cold War, which affected physicists in many parts of the world, certainly in the United States. And again, that list, of course, can also be extended. So one of the things I've been really curious about for a long time with my historical work is this question here. How has the scientific community, this intergenerational community, grappled with these very, very strange, deep conceptual uncertainties while immersed in this world that was no more certain, a social and political world that had its own sets of uncertainties as they were evolving in different ways in different places over time as well. I want to start by reminding the non-historians in the room, this will be very familiar to many of our audience members today, but might not be so clear to others. The period that occasions our joining together today, 100 years ago, the earliest formulation of what we now call quantum mechanics, that remains one of the best documented episodes in the entire history of science. We can vote about which is the best one, but this would certainly make the short list. There were tens of thousands of letters, often very informal occasional letters and postcards, as well as very deep and thoughtful and sometimes emotional letters traded among an entire core of people, many, many of which have been survived, published, translated, kind of poured over and over again, a kind of a historian's dream of primary sources. Hundreds of journal articles that are still in our libraries, dozens of monographs and textbooks from this very earliest era or thereafter. And then, again, as many of you may know, an extensive oral history program that began in earnest in the early 1960s, when many of these folks who'd been very young in the 20s were luckily still around to share their memories and recollections with people like Thomas Kuhn and John Halpern and Paul Foreman and others. And so these, I say, this is just a sampling of some of the kinds of materials that we historians get to benefit from to this day. The original letters collected, annotated, and poured over. Those sources have continued to support a robust, I'd say even flourishing genre of book-length scientific biographies of people from this era in the early days of quantum mechanics. And again, this is certainly a partial list. Many of you will notice my lists are tilted toward English language because of my own limitations. It's not meant to say there's nothing else important done in the field. But we have this still emerging body of work that I find myself going back to time and time again. And of course, a still much more broad and wide-ranging literature on the history more broadly, beyond merely biographical. Again, clearly just a selection here, but a selection, again, that I find extremely informative. And these historians and philosophers and scientists themselves have been going through conceptual histories, and of course, we still disagree. The latest book that I have found very useful was published in 2 very large volumes roughly 1 year ago. This is still a live topic for many of us. Social and political and institutional histories, pedagogical histories, lots and lots of ways to try to slice through and try to make sense of that enormous base of letters, publications, textbooks, oral histories, and beyond. And of course, that's just for this earliest period of what we might consider the first formulation of quantum mechanics in the mid-1920s. Over the years, many historians and philosophers and scientists themselves have traced how quantum theory itself, much like in the paths in Richard Feynman's famous path integrals, have proliferated, have scattered and zigzagged far beyond even the original formulation of quantum mechanics. As physicists of later generations came to formulate quantum field theory, there's now a robust scientific literature and historical literature on the early days of field theory, on its extensions and the critical use of quantum concepts, sometimes not always so self-evidently, in nuclear physics, in high-energy particle physics, in areas that were first known as solid-state physics, now the much larger world of condensed matter physics. Also, even a flourishing, I'd say, subgenre in trying to study the foundations of quantum mechanics and which generations have worried in which ways about the topics that had kept people like Niels Bohr, a very young Werner Heisenberg, Aaron Schrödinger, and others up at night. So that story hardly ended in the mid-20s either, and I'll pick up with some of that later this evening. Of course, I can't possibly try to go through all of those very wonderful and sometimes conflicting stories that all of our colleagues have put together. I want to zoom in on a certain kind of story that I find especially telling and very informative, that I've focused on a lot of my own historical work. That's a question that's really about institutions and ideas, about how do we make a community of mechanics, that is to say, how do we make people who will delve into the quantum realm with their work, with their thoughts, their experiments, and often their arguments. So what special and indeed very rapidly changing set of institutions of pedagogical ideas and so on has sustained multiple generations of scholars who've grappled with all these very wonderful but very strange features of quantum theory? And here again, I'm building on, I think, a very rich literature within the history of science, taking pedagogy and training as our main lens. Okay, that's my warm-up. What am I actually going to talk about tonight? I will talk briefly about this early era from really 100 years ago, I'll start really in the mid-1920s. Here again, drawing especially on work by several colleagues who are even in the room this evening. Then I'll jump ahead and look at some of the ways this work was migrated within the heads and on the scratch pads of young people who came over, in this case, to the United States, in the early middle decades of the 20th century. And then I want to close with a more recent history, going even later into the 1970s, because this quantum story was hardly done in the 20s, the 40s, it's certainly not even done today. So I want to look at these 3 moments with this combined lens of ideas and institutions. How have generations come to grapple with quantum theory, and why might it look different in different times and places? So again, I'm now drawing especially on work by Helga Krag and Alexei Kozhevnikov, and among many others, just to get a quantitative sense in our day of archive, where the preprint server gets 5 new papers per hour in many subfields. It wasn't quite like that, but this new field of quantum mechanics was really bursting. For the rates of scientific publication at the time, this was unusually rapid. And again, colleagues have been able to shed some light on that. So in the year and a half, starting with July of 1925 and thereafter, there were around 200 research articles grappling just narrowly with this new quantum mechanics, let alone the broader world of, say, atomic physics. Those 200 articles were contributed by around 80 authors, the vast majority of whom were quite young, less than 30 years old, fewer than 5 years past their PhD. They were in what we would now call or recognize as a postdoctoral career stage. That's why you might have heard this work was sometimes called Physik. I think thanks to work by people like Elise Krull and others, recognizing some of the young women who are also deeply involved in this, we might rather call it Kinderphysik. The point is, these people were children. They were very young, often in their early, let alone mid-20s. So people like Wolfgang Pauli and Werner Heisenberg, they were actually representative of this kind of work generationally. They were really in their early or mid-20s when much of this was happening. And some other names that we pause over, like Albert Einstein or Max Born or Erwin Schrödinger, they were actually the oddballs generationally for this work. They were already mostly in their 40s. They were a generation older than the majority of the folks producing this outburst of articles over here. And yet, when we zoom out and say, what was the typical career path? What was the way these people were doing their work day by day? It's actually the older folks who were more typical broadly. So we have the quantum mechanics authors being the exceptions in terms of career path or stage of career. And people like Einstein or Born or Schrödinger, despite their other very important conceptual disagreements and distinctions, they were actually in the typical mode. And so we start to see a kind of institutional divergence that, again, people like Helge and Alexei and many others have been able to work with as historians. So for the 50 years prior to this period, there had already come together a kind of expected or typical career path for academic research scientists throughout the German-speaking universities and beyond. Again, that might be familiar to many of you in the room here. I have to remind my own students and colleagues in the United States because it's not what we grew up with over there. The idea was there would be a graduate student assistantship, a PhD dissertation, and then, of course, as you know here, a habilitation, Privatdozent, to give you the right to collect student fees to give lectures. And then for a much more restricted group of the successful few, an extraordinarius professorship, and an even more restricted few, the ordinarius. And that really had become a typical routine even by the 1870s, certainly well before the 1920s. Again, as many of you might know, the ordinarius, the very senior professors, did more than simply advise their younger colleagues. They really had an extraordinary amount of control. They had control over the topics of the younger colleagues' research, over what they taught and when they taught. They even had to grant permission to travel or even to publish. It was often the institute director, ordinarius, who submitted their younger colleagues' papers to the journals. Right? This is now ready. I will send it. And so this was the sort of recognized norm by the time that very young Heisenberg writes to his parents in November of 1923. As you can see, as long as I'm here in Göttingen, I must do what Max Born wants, as the ordinarius, just as I had to do what Arnold Sommerfeld wanted to do in Munich. And he wasn't saying, I don't think he's writing that to complain. He's saying, this is just, as we know, this is the system. This is how it works. That system was about to come under some extraordinary stresses, again, because of things well beyond the very narrow world of academic physics. Again, I'm sure well known to us in the room. So a kind of drumbeat of events that I want to remind us of because they were setting important things in motion just at the time when very young Wolfgang Pauli and Werner Heisenberg and their colleagues were about to finish their PhDs, undergo habilitation, and join this quantum adventure. So, of course, the First World War had devastating effects in many, many parts of the continent and beyond. Within Germany, soon thereafter, the runaway hyperinflation, which really starts to become unbearable as early as 1922 and didn't stop then, was still roaring ahead into the mid-1920s. You see these stacks of the new marks in the Reichsbank. And then more narrowly within the sciences, again, as might be known to some of you, there was an overt, explicit boycott of German scientists by scientists in the Allied countries that lasted for fully 8 years after the armistice. And that had a very dramatic effect in who could gather in person to discuss these new, exciting, uncertain developments in areas like quantum theory. So this, you might take a quick look and think this is the famous Solvay conference photo of 1927. It's not. This is the photo. You can see it's fewer people there. This is the Solvay conference of 1924. There were 2 Solvay conferences held in the mid-1920s, which were meant to be the carryover from the pre-war Solvay meetings that had really helped to consolidate this early quantum theory community. And in the mid-20s, conspicuous by their absence were any scientists from Germany. At one point, the organizer tried to invite Einstein, make an exception. He declined because of the boycott. This went on for a long time. I point, at least in the English language work that I still find very helpful on this, by our colleagues Dan Kevlis and Paul Foreman, and of course many others. So this is now something, when we think about what's going on in the world of quantum theory research, it's not happening, anywhere or in a vacuum. It's happening under very, very fast-moving changes institutionally. Now, the hardest hit within this German system by these very rapid-fire changes, especially hyperinflation and the boycott, were those younger students or early career physicists who were just nearing habilitation or Privatdozent. It does you no good to collect student fees if no students can afford fees. right? If the marks have become basically useless. This starts affecting just even mundane daily things. This is now a well-known letter, a well-known situation when Niels Bohr invited the very young Wolfgang Pauli to come visit Copenhagen, de Boer's brand new institute in Copenhagen in September of 1922. Pauli had to write back saying, because of inflation, I can't even afford train fare. And so Bohr had to send Danish crowns as opposed to German currency so that Pauli could just physically get to Copenhagen to take up this, as I'll say more in a moment, this very new, somewhat unusual type of visiting fellowship at Bohr's institute. And this this concern lingered well beyond just getting to Copenhagen. There's a letter, again, well known to the historians, that Pauli wrote to his Doktorvater, to Sommerfeld, from Copenhagen a few months later during this same visit. And so Sommerfeld said, basically, it's time. You should come back to Munich, habilitate. It's time to move on. And Pauli says, essentially, well, it's really a difficult question, largely because he saw no particular career future for himself, given this extraordinary and very rapid set of changes in the academic system, which otherwise Pauli had assumed he would go back to and hope to flourish in. So he says, I can't stay in Copenhagen forever. He was on what we would now call a soft money, short-term visitorship. And yet Bohr has offered maybe to extend the short-term thing a few more months and so on. So you can see Pauli's sort of hedging to return. And the last part, of course, I find funny, but also a bit heartbreaking. What will happen later after the short visit, Pauli writes, I know just as little as an electron knows where it will jump after 10 nanoseconds. So where was it that Pauli was writing that letter from? Of course, it was the renowned, to us now, renowned institute in Copenhagen, originally known as the Institute for Theoretical Physics, now, of course, known as the Bohr Institute. Niels Bohr was able to found this institute in Copenhagen starting in 1921, largely because he was not yet a very, very senior scholar. He was we might say early to mid-career scholar. And yet he was able to convince the Danish political authorities that their very reasonably small and previously neutral country during the war could now play an outsized role in a kind of scientific meeting ground under the conditions of the boycott by the Allies. So this was a place Bohr convinced the authorities, successfully convinced the Danish authorities, if we make a special meeting ground, a literal meeting ground, for young colleagues who are coming from many, many countries who otherwise aren't going to be able to meet at Solvay or other kinds of places, then this otherwise not particularly central place could play an outsized role. This table I take from Helga Krag's book. There's actually a much more extensive, a whole set of many pages of appendices in Alexei Kozhevnikov's book that is too long to put on the slide. But what I want to focus on here, even from Helga's version, look at the range of countries represented. Right? Countries that had formerly been neutral in the war, countries that had been on different sides, literally warring sides. Here they can come together in Copenhagen because of Bohr's farsightedness and the support of the local government. He got much more support, and here again I'm drawing especially on Alexei Kozhevnikov's really just wonderful work. Very soon after the Institute was founded, it got a terribly important infusion of cash, sort of just the right moment, from a U.S. private foundation, the Rockefeller Foundation. The foundation had just started its new IEB, or International Education Board program. It's private money from the U.S., not U.S. government. And the idea was to basically fund fellowships, short-term postdoctoral fellowships, so people could come and have a kind of 1 year or 18-month stay, not have to follow only the familiar system of habilitation privatdocent and maybe or maybe not extraordinarius. This system was becoming more common in the US, not widespread, but not brand new, and I'll say more about that soon. This was not at all the typical pattern within much of Europe. And so it was this infusion of cash with this place that existed at just the right time, and that's why we can have these lists, as people like Helga and Alexei can compile, that have this really unusual, I'd say remarkable collection of people who can literally rub elbows at a blackboard or even at the basement laboratory in the Institute in a way that they were not able to do for much of this time otherwise. One of the very first visiting postdocs on this external soft money, on the Rockefeller money, to visit the Institute was Werner Heisenberg, starting in September 1924. I think he had the second of these new IEB Rockefeller fellowships. So let's take this all together, and now let's talk about, with tongue-in-cheek, Heisenberg's own matrix, his institutional matrix, on the road to what we are here to celebrate, matrix mechanics. So he completes his dissertation under Sommerfeld in Munich at roughly the age of 22. There's a story that his biographer, David Cassidy, repeats that when Max Born was visiting in Munich and asked this very impressive young student, Heisenberg, where are you going next, trying to lure him to Göttingen, Heisenberg reportedly replied, I don't have to decide that. Sommerfeld decides that. Don't you know who the ordinarius is? So there's a notion of who's really in charge for next steps. Indeed, it worked out, so we know that Born did write to negotiate directly with Sommerfeld, not with Heisenberg, and such that Heisenberg then became an assistant and eventually habilitates in Göttingen soon after. And then he gets this sort of exciting opportunity from Bohr in Copenhagen for this IEB, the Rockefeller postdoc, to then spend time, many, many months in Copenhagen. They have to really negotiate, that is to say, Bohr and Born have to negotiate, not young Heisenberg, about how long can you stay, when must Heisenberg come back to fill in as Privatdozent to teach when Born's about to leave. They work out all this out. I love this letter from Pauli writing to Bohr. Pauli had already visited, as we saw, the previous year or two in Copenhagen. Pauli, very close graduate school buddy of Heisenberg's, constant letters, we know, back and forth, goading each other on and so on. Pauli writes to Bohr saying, I'm so glad young Heisenberg come to you because he'll learn different kinds of work. He'll learn a different style of doing physics, and a style that at least Pauli was convinced Heisenberg needed. He says Heisenberg was so unprincipled, he grabs things from anywhere. You, Niels Bohr, will teach him a proper philosophical grounding to his physics, which will be different from what he learned with both Sommerfeld and Born. That's only possible in this very surprising conjunction of these institutions undergoing change, an external source of support, and this importation of a postdoctoral phase. Okay, he goes back as negotiated to Göttingen. He actually fills in because Born then leaves for an international lecture tour. As soon as the semester is over, thank goodness for the world, although it was bad news for him, he suffers this now very famous attack of hay fever and leaves town to Helgoland. His roughly 10 or so days in Helgoland only makes sense because of this kind of matrix of movements and institutions. So his sort of aha moment was really revealing the prepared mind. This was really, he was in the right series of places, having the right kinds of conversations of the sort that were not so typical beforehand. Comes back to Göttingen, Born, not Heisenberg, submits the paper to Zeitschrift. And then, as previously negotiated, Heisenberg then can take a few more months of this special Rockefeller-funded time in Copenhagen. He leaves very quickly Göttingen to go back to Copenhagen a few more months. It's during that phase that Born then, as ordinarius, submits both the Born-Jordan paper and then the Drei Männer Arbeit. So this is this is an unusual set of steps. Today, this might look actually quite familiar for our younger colleagues. This was not the typical path and was made possible for good and for ill because of broader worldly events. I just want to wrap this section up by quoting once again, actually, from our colleague Alexei Kozhevnikov in his really lovely short book, Copenhagen Network, you might enjoy. He just brings together all the different factors that had to happen for us to be here tonight to celebrate this kind of event in 1925. So just reading from Alexei, the path of a peripatetic postdoctoral fellow made possible by German inflation and Rockefeller money submitted Heisenberg to a variety of intellectual encounters and influences, Sommerfeld's thorough training, Born's proposal for a fully discontinuous quantum mechanics, which he'd embraced even more strenuously than Bohr. Bohr and Kramer's working out with the virtual oscillators, the so-called BKS theory, just as Heisenberg arrives. Pauli's very spirited rejection of visual models of electron orbits, Ralph Kroenig's calculations of intensity of spectrons. Heisenberg's is exposed and immersed in that kind of matrix because of both intellectual and institutional reasons. Okay, let me switch gears. Let me jump ahead a little bit and bring the story across the Atlantic to the United States. So quantum mechanics begins to migrate in many, many parts of the world, as we know, very quickly. My dear colleague Kenji Ito has written about the young Nishina's work from Japan and how Nishina studies in Germany and then brings many of those ideas back. So there's many, many directions and vectors that the broader scholarly community has charted. I want to zoom in now on the United States, the material that I happen to know better. So soon after the conclusion of the First World War, the United States National Research Council was formed as an advisory board to the National Academy of Sciences in the US. And one of the first things they did after fighting had stopped was to begin working again with these private foundations, Rockefeller, and then soon after when it was founded, the Guggenheim Foundation, and many smaller foundations as well. The idea was they were deeply concerned by the advances that many countries, including Germany, had made industrially, as was revealed during the war. And they worried that the United States had lacked this kind of coordination between natural sciences research, practical application, military usefulness. So the NRC says we're going to get private money to send a new generation of young scholars to Europe, either to do their PhDs or their postdocs. And they'll be funded by places like the Rockefeller or Guggenheim or others. You can see the list of people who then go just specifically to study in physics and physical chemistry. These are the first people who become based in the United States, who become sort of experts in the new quantum theory. They're often learning it in real time in places like Göttingen and Copenhagen and Munich and Cambridge and so on. And they come back and become, many of them, extremely influential kind of program builders and scholars in their own right. One of the names you might have noticed there, of course, was Robert Oppenheimer. Oppenheimer completed his PhD under Max Born in Göttingen. He originally traveled to Cambridge, England, had a bad fit, left, or maybe did not leave a poisoned apple, with all the stories like in the movie. Anyway, he quickly moved on to Göttingen and did his PhD under Born. He arrived about 4 months in Göttingen before Born suggested haltingly in a footnote the first time that maybe this strange shorting wave function is related to probabilities by its absolute square. That's in a footnote in June 1926. Oppenheimer was a young PhD student as Born's working that out. Oppenheimer is just completing his dissertation the next winter and spring as Born's younger colleague Heisenberg first introduces the uncertainty principle. Oppenheimer is right there immersed in exactly those discussions. After a very brief postdoctoral phase of his own, he's hired back in the United States at 2 universities, which is very rare then or now. He was such a hot commodity, the Americans would say. He was hired at both California in Berkeley and California Institute of Technology. I want to remind you, those are 600 kilometers apart. And as you know, Americans in Israel don't like trains. It's hard to get back and forth up and down the coast of California. And both schools were so desperate to have this young, extraordinary talent that they both let him take both offers. And he and his soon adoring circle of graduate students and postdocs would just caravan American style in their cars up and down the coast every other semester, often with the top down with the wind blowing. It's very California. Okay. Right away, Oppenheimer begins offering a graduate level, postgraduate course for the PhD students in quantum mechanics, among the first in either of his departments. It becomes wildly popular. For the very first time, it turns out, the grad students complain to the department head, he's going too fast, we can't follow. Oppenheimer says, I'm going as slowly as I possibly can. You can imagine this mismatch. He gets the idea, he gets a much better pedagogical rhythm, and quickly it becomes just a renowned course. Students take it for credit and then take it again and again. And again, the story is as related, in particular by his biographers, Marty Sherwin and Kai Bird. There was one grad student who was so insistent to take the same course for a 4th time, which Oppenheimer said, no, you've had enough. That she went on a hunger strike to take this course. And he finally relented. He said, okay, you can audit the course. 10 years in 1939, a different one of his PhD students, Bernard Peters, transcribed the lecture notes and made an early version of a kind of mimeograph called a hectograph. So they were easy to duplicate the page, the handwritten pages and typed pages. And they began to circulate. And to this day, they survive in many, many dozens of physics department and university libraries across the US. They were sold at cost for $1 or $2 well into the 1950s, even after there were many, many very polished textbooks. Oppenheimer's lecture notes for the American community became incredibly important and had a lifetime even after he had left the classroom. So we can read, how did he approach, at least by the late 1930s, these questions of this new body of material, quantum mechanics. The lecture notes bear clear marks of his own training in Göttingen and the conversations it had during his fellowship years. He lingers. He seems to just delight in the conceptual subtleties like Born's probabilistic interpretation, the fall of determinism, all these sort of efforts that had started coming out by the later 20s, especially the Soviet conferences, to try to circumvent Heisenberg's uncertainty principle, why they would always fail triumphantly. You can almost imagine the theatricality of Oppenheimer going through these. It shows up on the page. It wasn't only Oppenheimer. You see the first English language textbook on quantum mechanics published by US-based physicists. This book published in 1929, simply called Quantum Mechanics by Edward Condon and Philip Morris. They also had been beneficiaries of this NRC program. They'd also learned quantum theory in Europe on those fellowships and come back and become very influential teachers in their own right. They have whole sections that we might really rightly call the philosophy of quantum mechanics. Of course, they're introducing the Schrödinger equation. Of course, they're introducing the problems that we still teach our students, the particle in the box and all that. But they pause to say, how do we make sense of this strange-looking formalism? One of my favorite passages, they do the hydrogenic spectrum, all the Laguerre polynomials and so on. And they pause to say, well, be careful. Don't think that any of these things are real, because for an unperturbed hydrogen atom, they're all degenerate. So don't think that a state with, quantum numbers L and M different from its neighbors are somehow a different real state of the world, because they have no operational distinction until you start poking them with various kinds of fields. It's remarkable to pause in the very sort of familiar looking derivation of the wave functions for a single electron hydrogen atom, where they're saying, what's the status of this piece of the formalism? Again, very much like Oppenheimer was doing in his class as well. Another example, Edwin Kemble published a long kind of review article that was used as a textbook in what would soon become the Journal Reviews of Modern Physics. In 29, it was still called the PhysRev Supplement. He announces right in the opening paragraphs, there are philosophical difficulties in quantum mechanics that he says are a brute fact that we simply can't wish away or exercise as if they were a demon. That was true even in more informal pedagogical settings. One of my favorite sources I got to use as an historian are a collection of communal notebooks that survive in the archives of Caltech in Southern California, the physics department. They mark 40 years, from 1929 to 1969, of PhD students in the physics department writing down how they prepared for their oral exam for their PhD, and then reporting what questions they were asked, what responses they gave, and how different faculty responded. And it was almost like samizdat. They would hand them, under cover of darkness to the next kid so they could cram for their exam. This happens for over 40 years. It's a remarkable collection for historians. Throughout the 1930s, you see them scribbling down questions like this in their examinations to get their PhD in physics. What's the interpretation of the wave function? Does the Schrödinger equation describe the rate of change for all time? What about this sort of strange discontinuous behavior during measurement? Discuss the nature of observation or measurement in quantum mechanics versus classical mechanics. They have to give a kind of oral presentation on, again, what we might recognize as philosophy or conceptual foundations in order to get their PhD from Caltech, as well as calculate things like the hydrogenic spectrum. Well, sometime later, after the end of the Second World War, Oppenheimer, of course, by this point was a very well-known, internationally known figure. He was invited to give these Reith lectures on the British BBC in 1953, and they were published very soon afterwards in a lovely book. And he begins a section to describe quantum mechanics, saying that at least in the United States, quantum mechanics is no longer taught as a great adventure in human understanding, but instead, he said, as a set of techniques, an instrument of the scientist to be taken for granted and taught as a mode of action as we teach our children to spell and add. This kind of adventure, can we overturn the uncertain principle? Can we do something magical or strange? He at least was convinced that it kind of been bled out of his colleagues' teaching. He wasn't wrong. We can go back and look at the book reviews of the latest textbooks aimed at, say, PhD students to teach them quantum mechanics in the 1950s. And time again, there are many, many books being published. The reviews now praise the books that, quote, avoid philosophical discussion, or that, quote, omit distracting philosophically tainted questions. Our own former colleague at MIT, Hermann Feshbach, storms in this review of 1962 of the English translation of the French book by Albert Messier. Enough with this musty, atavistic to-do about position and momentum. We have calculations to get on with. That's essentially the message. Go back to that source, those Caltech grad student notebooks. You see students in the early 1950s being caught by surprise because they'd read the accounts from the pre-war, interwar years. They knew to practice on these strange kind of quantum phenomena, and they report this to the next colleagues who will read their books. The effort invested in analysis of paradoxes and queer logical points was of no use in the exam. Don't bother, right? Another student says, here's the best advice: memorize and rehearse the same stock problems, give the usual spiel. And you see that again elsewhere in more formal pedagogical settings. So what had changed? What had happened between the era of Oppenheimer and his students hanging on every word to this era in the 1950s and beyond, at least in the United States? Well, in brief, we know some things had happened, and here's just a quick reminder. Oppenheimer himself left the classroom and became the scientific director for the wartime Los Alamos laboratory. Here is shown with General Leslie Groves inspecting the Trinity's test site after the first detonation of a nuclear weapon, just weeks before similar weapons were used on the cities of Hiroshima and Nagasaki. The so-called Smythe report by the Princeton nuclear physicist Henry DeWolf Smythe was cleared for publication in advance whenever the bombs were used. Groves wanted to have something that could be shared with the public and the press, and that was Smythe's wartime duty. And this, again, I'd be happy to talk more about this. This report intentionally exaggerated the role of theoretical physics because that, it turns out, was easiest and most safe to share. And it downplayed all the very complicated metallurgy and chemical engineering and how do you separate isotopes and how do you make plutonium, because they didn't want to share that yet. So this is the one official cleared source on how these very strange and dramatic weapons had been made, makes it look like a circle of theorists in Los Alamos. And of course, it was 100,000 people, most of whom were not theoretical physicists. This has an outrageously immediate impact on policymaking in the United States and beyond. And one thing that happens, among many others, is that you see classrooms like this. Here's Richard Feynman at Caltech. Here's Tony French at MIT, teaching not to a dozen or 2 dozen students, but to hundreds, soon to many hundreds of students in tiered auditorium-style classrooms, because the demand for physics and for physicists had exploded, especially in the United States. I stare at this plot a lot. This is showing the number of PhDs in physics per year, granted just within the United States. You can read out sort of the changing political economy of the Cold War by looking at the sort of, bumps and wiggles of this plot. So just to orient ourselves, the Second World War ends here. You see lightning growth. I'll say more about that in a moment. The US enters the Korean War. You don't see a demobilization. And then you see the one American response to the surprise launch by the Soviets of the Sputnik satellite, another burst of just runaway exponential growth. I'll come to this part later, the downfall. Now, one might say, oh, but wasn't all of American higher education growing like crazy? What about the GI Bill? There was special funding from the federal government for many people who had served in the war to come back to higher education who might not otherwise. True. So here I've normalized, this is now all PhDs as if they'd had the same numbers, only physics. And you can see this is also an exponential burst. The exponent is 1/2. If you have several time steps with an exponent that's twice as big, you see an enormous divergence, right? The rate of growth in physics outstripped that of every other field in the American Academy for several years after the war. Likewise, again, after this burst of funding in the late 50s, a second kind of Cold War burst. It's also, by the way, not because of demographics. This is the population of the US, age 25 to 29, typical age for doing a PhD, not exclusively, but typical. And that's actually falling as a proportion of the US population, just as the proportion of young physicists is growing. This is not about more young people. It's not because all of higher education is growing. It's because of very intentional shifts in policy and a kind of attractiveness to many young people of going into physics. This was, again, kind of amplified over and over again by officials in the Atomic Energy Commission, the carryover from the wartime Manhattan Project, by officials in the American Institute of Physics and elsewhere. They began talking about young grad students in physics as basically a wartime commodity. It's like a short commodity like rubber or tin that should be assessed, stockpiled, and rationed. They're talking about young grad students here, not just gasoline. They start printing notices in some of the earliest issues of Physics Today. The magazine began in 1948. By the end of that year, they're printing notices to faculty members to start draft deferment proceedings on behalf of their students right away, even before the Korean War had started, whether the student wants to be drafted or not. Physics students are more valuable, the argument was, in the classroom than in any other thing they might do on behalf of national security. So get them deferred from the draft, whether they've asked you to or not. And this is all before and during the Korean War, and then again, a burst of this in response to the Sputnik launch by the late 50s, and again, largely funded by, in the US, the so-called National Defense Education Act, passed into law less than 1 year after the launch of Sputnik, which made enormous amounts of funds available for training in particular so-called defense-oriented fields, which meant physics and the physics-based engineering fields, and language instruction, as long as it was Russian. Couldn't study French on this. Okay, so what happens now? Let's go back to these physicists who are encountering some very rapidly changing institutions within which they're trying to make young quantum mechanics. So I did a study of all the complete sets of lecture notes I could find. There could well be more out there. These are complete notes, not formally published, still as prepared either by the instructor or by one of the students, from across across about a dozen physics departments in the US over the course of the 1950s. And the departments ranged in many ways, but these are all courses meant for first-year PhD students, postgraduate students, taking quantum mechanics. And you can go over page by page and say, what proportion of that classroom material is devoted to the kinds of things that Oppenheimer and Condon and Morse and others had lingered over, what we might consider kind of philosophical or conceptual foundation of quantum mechanics. What might that correlate with? The one thing I could find with which it correlates was enrollments, was class size. And so I very loosely split up into sort of philosophical, we might say conceptual emphasis classrooms, and the kind of pragmatic classrooms. And this is not good, bad. I'm not saying there's only one proper way to teach quantum mechanics then or now. I'm saying you see a difference in pedagogical choices, a difference in things to emphasize both in class and on the accompanying assignments that correlates with things like what's it like to have an informal discussion about the fall of determinism with 12 people sitting on their desks versus 100 people taking notes. It's a different pedagogical challenge. So again, I want to be clear. I'm not saying this is the best way to teach it and this is the wrong way. I'm saying these are different choices that lead to different emphases and different kinds of intellectual paths. Now, that's clearly a small sample. Nonetheless, as I say, there's no correlation with, for example, what was the instructor's wartime experience. There were people who were teaching highly philosophical classes who had led whole divisions at Oak Ridge National Lab during the war and vice versa. It wasn't where the instructors themselves had trained. Some had been trained in Europe, some trained in the US. It wasn't where their department's own graduates got jobs. We can track that because these physicists were in such high demand. We have all these sort of registries of where practically every scientist for a long time in the States completed her or his training and where they got their jobs. We can correlate sort of employment, doesn't correlate with that. It really correlates, at least from this small sample, with enrollment, with class size. Then I wanted to do a bit of a more longitudinal study. So US-based physicists published 33 graduate-level textbooks on quantum mechanics over the next 30 years after this time. Textbooks that, again, according to their own preface and as reviewed in journals like Physics Today and American Journal of Physics, were explicitly geared for first-year postgraduate students. In the US, we'd call them first-year PhD students, essentially master's students, typically here. So with the help of many very dogged research assistants, we then Xeroxed every single homework problem that's in those books. It's 6,261. It's actually about 400 problems repeated over and over again. You can predict many of these problems, the standard ones. And then we coded them. Well, are they asking the student to respond in sentences as a sort of short answer or only calculation? Again, it's not good, bad. Saying what type of skills were being emphasized pedagogically. And so starting soon after the war, the proportion that calls for a kind of qualitative or conceptual response lingers around 10%. And then after this crash, I'll say more about this crash enrollment soon, that proportion itself jumps to nearly 50%. That's an enormous change in a series of books over not a very long time period. So George Uhlenbeck, of course, originally on the continent and had moved to Michigan even by the 1920s, he was not so happy about this. So Uhlenbeck writes a review of some of these trends. He says his colleagues in the US had confused what he called what was easy to teach, the technical mathematical aspects of theory, things we can put onto problem sets and grade sort of in bulk, confuse that with what the students needed most, at least according to Uhlenbeck, more of a focus on concepts. And again, we can look at kind of pairs of textbooks that mark out this fast-changing terrain. In the US, I think the perfect pair to look at is a book by Leonard Schiff, simply called Quantum Mechanics, and a book by David Bohm called Quantum Theory, published very close to each other in time. Both of them had been younger physicists under Oppenheimer's direction at Berkeley in the 30s. They both published these widely acclaimed books soon after the end of the Second World War. They were very different. And so just to boil it down, Schiff's book is the kind of emblematic of this practical, instrumental, teach things that students need to calculate. The Schrödinger equation appears on page 21. All the stuff that he'd heard Oppenheimer lecture about, the fall of determinism, can we do an end run around the uncertainty principle? He dismisses that or dispatches that in a few opening pages, essentially in a preface. Contrast that with David Bohm's book, where the Schrödinger equation doesn't appear until page 191. Right, page 21 versus practically 200 pages. That tells you, at least what these instructors think is important to focus on as a teacher of quantum theory. Bohm's book quickly goes out of print. He applies to publish a second book that was rebuffed by the American publishers. Of course, as you may know, he has other political drama. He actually essentially has to leave the country because of McCarthyism. Again, I'm happy to say more about that. In the meantime, Schiff's book becomes the industry standard in the United States, goes through 2 subsequent editions. In each one, the book gets longer, that's typical, with more very clever, carefully crafted homework problems and less conceptual discussion even than prior. And then, as I say, after the crash in enrollments, you see a new generation of books that have 50% or more that have what we might call discussion questions. The student has to answer in sentences, in paragraphs. They also, of course, have many questions where the student have to calculate. Again, it's not just in the formal teaching materials. Here's a case just to bring it a concrete local instance. A tenure case at the University of California at Berkeley in the mid-1950s. Young instructor Roland Good Jr. was working on foundations of quantum field theory quite early. This is the early days of renormalization. He was fascinated by that. And yet he was not promoted. And there's a paper trail. It's very hard not to promote someone. And so that generates lots of paper that historians sometimes can look at. The department head was very quick to say he's a gifted teacher. He's very productive. He's a good citizen in the department. He wasn't failing on the typical things. Here instead is why the committee chose not to promote this young researcher. It is not the sort of work, his choice of research topic, that can readily be used for PhD theses. Hence, it seemed to our committee that he was not carrying his fair share of the load of grad student research. It was therefore felt he would not be particularly valuable to us, since we have a very large number of grad students who must be guided to the PhD. You can't train dozens of people, at least the argument was, in the kind of critical foundations or philosophical approach to quantum field theory. Nearby at Stanford University, just also in the Bay Area, you see some dramatic shifts in the entering cohorts of their PhD program in physics over the years, where, again, this fall that I'll come to in a moment, the number of incoming students fell by half in about 3 years, right? That's quite dramatic. When the numbers were still growing and seemed unstoppable, many of the faculty then, as now, complained they have too much grading to do. Some things never change over time. Faculty always say we're too busy. So they decided not to have these very in-depth oral written exams for their students. They switched to easy-to-grade true-false exams. You could briefly get a PhD in physics from Stanford by answering true-false questions because they figured they couldn't grade too many more. Once the population has collapsed and very many fewer students come, they now make the general exam, the same role in the student's progress, 40% essay questions. And that same year, they introduced a new informal seminar called Speculations in Physics, essentially what had gotten Roland Good fired 20 years earlier. So let me briefly look at now this last moment. So I pointed out earlier there's this dramatic fall, this cliff that happens in this number of PhDs per year. And again, this is not surprising, certainly at least not with hindsight. We have other major developments. The first major budget cuts within the US on defense spending, which had been propping up research in areas like physics since the Second World War. That starts to falter by the mid to late 60s. And then you have really the slog, the quagmire of fighting in the Vietnam War, where at first the Department of Defense revokes the draft deferments for full-time undergraduates starting in 1967. Some students could still get deferments, but it wasn't an automatic. Then revoke automatic draft deferments for PhD students starting in 1969. And around that same time, there are changes in Congress about what kinds of money the military could spend in terms of academic or university-based research. Remember, this is showing number of PhD conferrals. If you have fewer people entering here, you'll have correspondingly fewer people graduating here. And it wasn't, as you can see, an adiabatic change, right? This was the bottom falling out. This was also happening at a time when many people, faculty and students alike, and community members, were very, very expressing, sometimes with marches in the streets, being met by police with clubs, concerned about the role of defense spending in American academia, in particular in American physics departments. This has, again, an amazingly quick and very crushing effect on young physicists, kind of like those who were going through habilitation under hyperinflation back in Germany. Here you see the job placement statistics from the American Institute of Physics, which used to run a clearinghouse to match young PhDs who were seeking jobs with employers looking to hire physicists across all three sectors: academic jobs for physicists, industrial laboratories, and government laboratories. Even as the number of young physicists was growing exponentially, the number of jobs grew faster in the sort of 10 to 20 years after the end of the Second World War. But you can see how quickly those fortunes reversed. So by the early 1970s, there were more than 1,000 newly minted PhDs in physics competing for 53 jobs on offer. Okay. So what's it like to make a career in quantum physics under those conditions? Let's come back to this sort of career path of young quantum physicists under now a very different and dramatically changed set of conditions. I want to tell you a little bit about Fritjof Capra, who's originally Austrian. He completed his PhD in high energy theory at University of Vienna in 1966, and then was hired as a postdoc after a sojourn in Paris. He was then hired as a postdoc in particle theory at University of California, Santa Cruz in the late 60s at a 2-year appointment. And then the money ran out, right? This is exactly when that crash just happened, as I pointed out. His appointment ended when there were essentially very few jobs left on offer. He arranged an unpaid affiliate position. He essentially had a desk in a mostly empty office in London at Imperial College for a few years. He knew the department head. The department said, I can't pay you, have a desk. So Fritjof, with a PhD and now one full postdoc completed, many published articles in the literature, he had to get by tutoring young students in physics and math, like high school age students. And then he began translating into German abstracts of articles mostly from English for the Physikalische Berichte, since his first language was German. And then he had an idea. He'll write a textbook. He loved teaching physics. He thought he'd write a textbook. He had in mind a book called Current Concepts in Particle Physics, which he thought would first pay him royalties, maybe even an advance from the publisher, and then would make him look like a more competitive applicant for a teaching position, a university position. That's his idea. He begins writing chapters on things like the uncertainty principle, very basic quantum phenomena, as before he even gets to more specialized topics in particle theory. And he sends these to more senior colleagues he happens to have met at conferences along the way, including Vicky Weisskopf, fellow Austrian, by this point, the recent Director General of CERN, a very successful textbook author many times over, a kind of grand elder statesperson of physics at MIT. And their letters survive. So Copper sends drafts of chapters to Weisskopf. Weisskopf says, I like it, tweak this, the kind of feedback we'd want from a senior experienced textbook author. And Copper says, well, thank you, Professor Weed. I really need help. I need to get money, right? How do I line up a publisher? What's my advance? How do I pay rent? These letters, they're remarkable to read. So Vicky doesn't miss this. He writes back in the midst of this exchange, I like your style in the writing and find many things well expressed. I would again encourage you to go ahead and finish the manuscript. I understand your need for financial support, but you should know the fact is a book like this is not going to bring in much money because of the nature of the subject. The best you can hope is something like $1,000 the first year and less thereafter. This will not be your ticket to a financial security. Copper is invited then to return back to California, to give some lectures with Jeffrey Chu's group at Berkeley, and visits his former postdoc advisor, Michael Nauenberg, at Santa Cruz, and has what he himself calls a transcendental experience on the beach. I don't know if many of you have been to Capitola or Santa Cruz. I can believe it, right, when I see these photos. Just this sort of, he lost his sense of space and time. He had really a transcendent experience. He wrote about it actually quite movingly. He then talks with his former postdoc advisor, Michael Nauenberg, about a different idea. If this textbook's not going to be his ticket to a secure future, and he's now gotten deeply interested, earnestly interested as a seeker to learn all he can about various Eastern kind of intellectual and spiritual traditions, Taoism, Buddhism, Confucianism, so on. He says, maybe I should write a different kind of book. He has all these vetted chapters on things like the uncertainty principle. He wants to do more reading about things like Taoism, Confucianism. He should write a different book, not an undergraduate textbook. And Michael says, yes, try that. And so he does. He writes it very quickly, The Force of Necessity. He then sees Vicky Weisskopf again at a conference. Vicky happened to be in California. He gives him a copy of the freshly printed book, and Vicky reads it on his flight back to the East Coast and writes this very sweet letter. I read a good part of your book during my flight back, and I liked it very much. It's very hard for me to judge whether you have succeeded in your task, since it addresses itself to a very specific kind of public than you find here in the East. Translation, we have no hippies at MIT. Okay, you can understand. I do believe, however, it's a very good book, and it'll be, there will be many people who will have a better idea of physics after they've read it. Very generous of him to say. In fact, the book becomes an unbelievable publishing sensation in many, many parts of the world. This kind of fawning coverage about Copper himself, about this magical meeting of the minds, it sells 150,000 copies in its first 2 years alone. I should say it was rejected by 12 publishers ahead of time, right? It's one of these wonderful kind of, in hindsight, a wonderful story. There have now been 43 editions in 23 languages, right? All my books together, you get the idea. It's not a good comparison on my side. What's really surprised me was the reception it received from a number of physicists. There were some physicists who wrote snide, sometimes fair, but very critical reviews. That didn't surprise me. I thought, oh, what's he doing, mixing these things? Keep them separate. What did surprise me were some of these responses. It actually had a longer tail. The official review in Physics Today says actually gets the physics right. That makes sense. He was writing a textbook, vetting it with senior scholars. And also, it couches this work, the reviewer says, in the immediate feeling-oriented vision of the mystic, so attractive to many of our best students in the mid-1970s in places like Ithaca. There was an even more interesting exchange over many years in the journal American Journal of Physics, which, as you may know, is dedicated in particular to the teaching of physics. So people want to share their best curriculum, their best lesson plan. They critique new textbooks. It's really about pedagogy for the physics profession. And you see a back and forth, almost like a Cold War within the pages of the journal. People first saying, should we use it? Maybe people saying we can't afford not to use it because it will get students back into the classroom at a moment, remember, when those enrollments had really tanked. So there's Professor David Harrison, who begins designing a whole semester-long course around this. And then someone says, oh, you shouldn't do it. He writes back saying, this is the reason people are actually taking classes in the physics department at all. Years after that, another kind of observer of this exchange says, even with the passage of time now by the late 1980s, it would be easy to dismiss these ideas entirely, dismiss this kind of parallelism of Eastern spiritual thought and quantum theory. But in doing so, you might risk alienating a newfound interest among students. This field has the potential of appealing to the imagination and to perhaps be carefully explored and maybe even exploited. Let's use this because physics is not in great shape. Other people thought about it more earnestly. The same David Harrison, who developed a course as early as 1979, begins teaching Bell's theorem and quantum entanglement in his undergraduate quantum mechanics courses before nearly anyone else, at least from what I could find in North America. It certainly was in 0 textbooks aimed at undergraduates, at least in English, this early. So he was so enamored of the topic, partly from having taught Copper's book, he developed a whole lesson plan to teach undergraduates Bell's theorem, Bell's inequality, and then he wrote it up again for this teaching-oriented journal in the early 80s. Well, it turns out, and let me wrap up and bring us not quite to the future, but a few more steps to the end. Another one of Fritjof's discussion partners in Berkeley during much of this time was John Clauser. There's a young Clauser shown here in the early 1970s, literally duct taping together the first laboratory experimental test of Bell's inequality. He was working with a grad student, Stuart Friedman, who was kind of loaned to him at the time by his supervisor. This was not at all what Clauser had been hired to do. He was wanted to do this for his PhD. His advisor at Columbia said, don't you dare. We don't do silly little philosophy here, essentially. So Clauser did a PhD in basically radio astronomy and cosmology. That's what he was hired to do at Berkeley. The crash hits. Berkeley's now deeply under capacity, and he says, can I spend half my time on this passion project of trying to grapple with Bell's inequality? And the advisor, Charles Towns, says yes. John said later, he got good at dumpster diving. He had no budget, but he could scrounge equipment from around the laboratory. 10 years later, of course, Alain Aspect and his team conduct a kind of improved set of experiments on Bell's inequality, addressing these so-called loopholes. Years after that, Anton Zeilinger and his group, and of course many groups by now around the world, I can't help but put on out of the timeline something that Arne mentioned briefly. A highlight, at least of my own life and certainly my career, was a chance to work with Anton on much more recent version of these things in just a few years ago. The point is, this becomes a thriving but small kind of sidelines tradition, dating from some of those same discussions that had inspired Fritjof Capra to write the Tao of Physics. Another member of this circle was Nick Herbert. Nick had done his PhD in quantum optics at Stanford, couldn't get a job. He graduated just when the bottom fell out. He was, for a few years, literally on public assistance, what we call welfare in the United States, after a PhD from Stanford, and bumbled along. And no one of these people just caught out of phase with this rapid shift in career opportunities. He would also meet every week on Fridays for years with Fritjof Capra, with John Clauser, and a small circle of others, Elizabeth Rauscher. And he also got completely enamored of this idea of quantum entanglement. What does this tell us about the world? What can we do with it? If entanglement is so wonderful, let's put it to work. That sounds familiar to us today. One of the things he wanted to do was design a device to signal faster than light. Now we can chuckle now, we know about no signaling. We know that because of these kinds of efforts. It was because of a series of thought experiments, one of them called FLASH, which was an acronym that he made up. This was the hand-drawn cover page of his preprint. You can see where Nick's proclivities lay. It's listed as an NSF preprint. That was not the National Science Foundation. He had no support. It was the Notional Science Foundation because he liked studying the nature of consciousness on the beach. Very clever person. This was sent out for review not from Physical Review, but from a brand new journal founded just in 1970 called Foundations of Physics, which catered a small little space for more overtly conceptual or philosophical analysis, at least within the English language. And you can see some samples from the reviews. People said either this won't work, but we can't figure out why, or people think this is going to work. We have to build this, right? This was then sent through a particular kind of paper trail network that I tried to retrace in my book to John Wheeler. Wheeler shared it with two of his youngest PhD and recent postdocs, Bill Wooters and Wojciech Zurek. And they began working. Wojciech very kindly shared with me his own personal notebook from that era. And the long story short here is that the no cloning theorem, at least the Austin, Texas version from Wooters and Zurek, was discovered in response to, as a way to try to break or figure out why we can't use entanglement to send messages faster than light. Quite marvelous. And then that was the last step needed, again, thanks in this case to John Wheeler, for people like Charles Bennett and Gilles Bressard. That was the last piece of their puzzle. They'd been wondering about, could we use quantum physics to send quantum encrypted messages? And they didn't have this notion, because no one did, until the early 80s, about what we now call the no cloning theorem. That was literally the last piece. Bennett was invited to visit John Wheeler in Austin. Wheeler says, have you seen this paper from my younger? Right. And here we have one of many steps, and an important step toward one of the first genuine quantum technologies, at least now on paper, quantum encryption. In parallel, actually quite separate from that, you see some of the earliest work now, what we'd recognize as quantum computing, or at least theoretical quantum algorithms. If one could keep a large collection of qubits stable, have them not decohere arbitrarily quickly, what could we do with that? Why could we compute differently with a collection of qubits than with a collection of classical bits? And then these different strands, which really were not much in coordination yet, were pulled together pedagogically in this magnificent book, first edition 2000, at least in English, called Quantum Computation and Quantum Information. And right in Michael Nielsen's and Ike Chang's preface, they say that quantum entanglement has become a fundamentally new resource in the world that goes beyond, essentially beyond classical resources. It is iron to the classical world's Bronze Age. So let me bring us up even more to the present with yet another MIT colleague. It's a very parochial talk. Our dear colleague Barton Zwiebach, his latest very impressive textbook from his 3-semester undergraduate course in quantum mechanics at MIT called Mastering Quantum Mechanics. Again, the very first words you find in Barton's book are these. After 100 years of quantum mechanics, we are still discovering some of its surprising features, and the theory remains the subject of much investigation and speculation. And so, as we all know in this room, the quantum adventure continues. Thank you.
Yeah, David, thanks so much for this very, very rich talk for a very, very rich quantum century.
Yes.
So I wonder whether we will have some discussion, some talk that can reach from the 1920s to the 2020s. If you have any questions, please raise your hands and wait until the microphone comes to you.
So my question actually goes from the 2020s to the 2120s.
Yeah, good.
In the sense that, well, Niels Bohr is known to have said it is difficult to make predictions, especially about the future. Right?
Yes.
So I'm going to ask you for one. So you examined some sort of effects of geopolitical developments. So what's your take on the current development, which in the new geopolitical context leads to quantum, due to what you have in your last slides, being considered dual use, to all this export control, which suddenly makes it essentially forbidden. I mean, like we have to segregate Chinese students. If we hire them, we have to, like really discriminate them and prevent them from attending our group seminars. What's your take on that, and how do you expect it is going to affect the world?
Good. Thank you. It's an important question. As you already noted, I won't make a firm prediction. None of us, I at least have no training to make a prediction, a useful one. But I share your concern, and it's a very real one. It's not only in the field of quantum technology, as I'm sure you know. I face this on the physics side, even working in what I would consider very beautiful and abstract studies of early universe cosmology and black holes, which, as far as I know, are not about to become a useful commodity. We haven't figured out how to do that yet. Maybe we will. But I think, so it's, the question is very real. I don't have a great answer. What I do worry about, I think I share your worry. Part of what mattered in each of these moments, at least as I look back on them, was the ability for young people to travel. Even in this wonderful world of Zoom, we got by pretty well during some hard times recently. We all know that's not the same, right? At least I don't think it's the same. Full, all the kind of Slack and email and Zoom, they get us a lot further than the absence of them. But there's still something about rubbing elbows at a blackboard or increasingly a whiteboard, right? Face to face over a couple of weeks or better yet, a couple of months at a time. And I think that's been true in each of these episodes and others that my colleagues in the history of science continue to explore. So, an answer to that is if we're going to have to become politically active or at least lobby with care, not careless, but with care, let's lobby for things like access and ability for people and ideas to travel. Does that mean every single thing should have unfettered access everywhere in the world? Okay, probably not, right? But is there a way to have some reasonable set of space for people and their ideas to move and interact and grow and return? Because once that starts getting tamped down, we have plenty of examples in history of where that does not lead us where we want to be, right? So history can't make us great predictors. It does, however, show that we have this amazing empirical database of human experiments, right? We've tried that a lot, actually. We tried it during the First World War. We've tried it before then. Some I work in separately on the early history of general relativity is all about who could receive a journal during the embargo, who couldn't even send a postcard during, again, the First World War in this case. What about Cold War classification in the US, right? It wasn't only overt wartime. We've seen this, we've done this, many of our communities, and I don't think in hindsight we love the outcomes every time. So to the extent that history can become useful as an empirical source, to say, let's at least be extra careful this time. It might not give us the one best policy to try, I don't think it will, but it might hopefully make us better attuned to what to watch for. And for me, I want to watch for the ability for young people in particular to get in a room for quite a while and talk, right? Not just on Zoom and certainly not only under embargo.
Are there more questions? Maybe I shift the discussion a little bit to the history again. Yeah. Before we all were reading The Tower of Physics by Fritjof Capra, we read Thomas Kuhn's Structure of Scientific Revolutions. Yes. in a nutshell, my question is, we have seen this big transformation of how physics was understood when it traveled to the US, in particular after World War II.
Yes.
The question is, how does this resonate with a shift also in the historical picture that was drawn in the US?
Oh, this might not be what you're getting at, Arne, but it might be. Here's my first take, and maybe this is what you mean. I mentioned very briefly, and only a few of my colleagues in the room might have noticed, one of the earliest slides mentioned the sources for history of quantum physics, in that first slide about the letters. That was one of Thomas Kuhn's first kind of big history efforts. It was funded actually, again, largely by private money at the time. And he was able to hire multiple assistants. In history, that was very unusual, at least in the United States. It was a big history because he had, 3 younger colleagues and another assistant. So he was immersed in planning for that as he was completing his book on structure. Structure was first published in 1962. They were conducting these interviews as early as at least I think 1960, certainly 61, a little bit earlier. I think now let me tell you, our colleague Mara Beller made the following argument. I agree with her, so I'm going to credit Mara for first articulating this. I think that much of the work in the history of science and the history of physics in particular had a kind of overreaction, thanks to Kuhn, because Kuhn made much of this himself, to the radicalness of the break in quantum theory and relativity, which is to say, I think Kuhn elevated these indeed unusual moments in intellectual history as if that's a recurring norm. and paid less attention to the various kinds of continuities, whether institutions or instrumental. In many ways, the Fuller community has filled out a kind of post-Kuhnian picture ever since. I think Kuhn was sort of primed for these dramatic ruptures, the Gestalt, where it's either a duck or a rabbit, and it switches overnight, mystically and without well-known rules. And I think, again, as people like Marabella and others have said well before, I think that might have been an earnest reaction to a skewed sample. Let's put it that way. So the fact that Kuhn was doing unbelievably foundational, important work for us in the history of quantum physics, he had the foresight to get resources, again, actually thanks again to John Wheeler, among others, and interview these folks who had been very active, and even the more older folks who were active in the 20s, when some of them were still around to talk with in the 60s, said, get their letters, get their notes, and talk with them. For that, I have nothing but great gratitude to this day for what Kuhn and his colleagues were able to do. Then that becomes built into a kind of template, a bit maybe artificially, or again, oversampling what turns out to be maybe an unusual set of these kind of dramatic conceptual breaks, and set much of the field of history and philosophy science looking for these ruptures or debating these ruptures. That became the thing to talk about for quite a while. And I think only later did we come to talk about other kinds of continuities or embeddings, institutions, and so on. That might have been an inside answer for the historians. That's my take on it, Arne. Thank you.
Thanks a lot.
Yeah.
More questions? Yep.
Thank you. Wonderful talk. This is a question about the middle part of your talk. You showed how the discussion of foundational topics in quantum mechanics, so present in the pre-war time and so absent in the after-war time, was reflected, for example, or you mentioned Oppenheimer.
Yeah.
Who lived through both of these times.
Yes.
So I wonder, how did he himself and other people of the time see that change?
Yes.
You gave us an explanation of, that is mostly structural, but how did they themselves realize? Did they realize, and did they see as a deplorable development or whatever? So
yes.
Okay.
Good. No, thank you, Friedrich. So for Oppenheimer, it's an easier answer because he stopped teaching, because at least in a formal way. So during the war, he was very busy with things we now know about. Very soon out, he went back to Berkeley to teach for not even 2 whole academic years. And by 1947, he was recruited to become the director of the Institute for Advanced Study in Princeton, New Jersey, which is explicitly not a school. There are no registered students. The first thing Oppenheimer did as incoming director was to increase by a factor of 2 the number of postdocs in theoretical physics, but they still were not, it wasn't a formal course. No, it wasn't right. And then even then, he was, until his infamous hearing in 1954, he was jetting, training down to Washington, D.C. He was much more involved with kind of nuclear policy and advising the government. So Oppenheimer essentially never taught quantum mechanics again, right, really. And he did, and that's why I found it so moving, actually, his very emotive language. I mean, he became, a kind of sage-like figure in the popular media well after that period, but even in the early 1950s, but even before he was kind of, so to speak, martyred with this famous takedown by the state in 1954, he's lamenting that he sees his colleagues, at least, having shifted too far, right? We have this example from George Uhlenbeck. Again, it's an unusual trajectory. Uhlenbeck, continental, has to flee the Nazis, resettles actually quite early. Actually, he relocated even before 1933. He says, you, my dear American colleagues, you're doing it wrong. But by the point, he'd been an American instructor for many decades. So I see moments of, we might call it disappointment, maybe not quite resistance. Then you see these pockets of classrooms that persist, but the ones that do, I'd say, are correlated, as far as I can tell, with the practicalities of teaching, what you call rightly a structural response, and less so with other things that I at least could find out so far. Very briefly, I know I've been talking for a long time. Lothar Nordheim was one of these European physicists who relocated to the United States. He ran a whole division within Oak Ridge during the war, handling isotope separation. He was as involved, or more so than Oppenheimer, in the kind of day-to-day technical things that many historians have said made all these American generation kind of merely instrumental, right? He was in that as much as anyone else. He teaches for a couple of years back at Duke University, North Carolina, which did not have the runaway enrollment as early on as MIT or Caltech or Berkeley and so on. And Nordheim, who just came straight from Oak Ridge and in fact goes back to an industrial position about 2 years later, very practical and applied, he's teaching this, what we might call philosophical approach in the 1950s, right? So that's, now again, these are small numbers, and to get away from that, that's when I try to do this longitudinal textbook. So that's the best I can do for now, Friedrich. But I think I see moments of comment, if not quite resistance, and pockets where a different tradition still can kind of bubble up.
Yeah, okay. After Friedrich Steile, we have Stephan Häusler.
Thank you for the talk. I also have a question on teaching.
Yeah.
Not teaching at university, but at high school. So for young people, what do you think is important to teach in high school? Is it rather the technical thing or the philosophical, the political? There are so many dimensions. Restricted time, very important. What would you suggest to teach?
Thank you. Well, again, there are many people who are experts in this, and I am not one. So I would first want to turn to those who have to do this every day. My sense, for reflecting on my own trajectory, is that it's not a surprise, we need some balance, some part of both. I had an unbelievably inspiring high school physics teacher. I mean, I went back for his retirement, and it was really the impact he had. I wanted for years to be a high school physics teacher, and he told me don't do it. He kept it out of sight when I had him in class, and I came back there. He said, no, it's a hard job and there's no money in it. He became very disillusioned. He was magnetic. I mean, he was one of these special teachers. We don't have enough, and when we have them, they can have this kind of impact. So he would lend me his books. He was going back to do a PhD after hours because he was still in love with the material. And then he would lend me his books. I couldn't possibly parse some of these graduate level textbooks as an undergraduate, but it was some of those from the 70s whose covers I showed that were filled with this qualitative discussion next to the things that were still too hard for me to do, as a teenager. And it was my bedtime reading. Maybe it's telling you too much about myself. This is very kind of kid I was. But I mean, I was just mesmerized both by this very inspiring teacher and by the fact that there were things to get excited about. And I can imagine a path that I know I can't do this yet, but look at this big fat 700-page book. There's something to, right? I also had to learn, at least some basic calculus and some basic classical mechanics, right? To be able to then do anything else when I became an undergraduate. So this is where I give the very not helpful answer. We need some combination of both under constraints while teaching for exams and all the rest. I don't have a good answer, but as long as this kind of spark, because there's an enormous universe out there. We do need to teach you elementary mechanics and elementary electromagnetics. We're not doing that for no reason, but there's also things to get a taste of, right? Whether it's the Big Bang or black holes or quantum entanglement or an enormous list. And so I'd like to think these days there are so many other resources online. Some of them maybe we don't want to endorse and they're kind of not so great, but a lot of actually pretty high quality things made by very engaging professionals who also have media training, right? We need that. So, my own kids grew up watching some very good, very short YouTube videos that I appreciated. And I had to, read a 700-page book under my pillow, right? So I have hope in that sense for the future. That means more of us should maybe invest in this kind of para-educational stuff so that the young people who are actually in the classroom can at least point to things, for free that our younger folks could say, oh, check that out. What do you think? We can come talk.
Wonderful. Are there any more questions? Okay, yeah. One just in the back.
Thank you for another great talk, which I really enjoyed. I would like to stay with the history of education, and I found it particularly intriguing how you analyzed the changes in teaching theoretical physics on the university level.
Yeah.
What I'm wondering is whether you find similar developments in the teaching of experimental physics and even broader asking chemistry, engineering. So is there some sort of changing mentality on how to teach science, technology, and engineering?
Thank you. It was a wonderful question. I don't have a good answer, but I have some preliminary thoughts, and hopefully others can help fill this in. One thing, there are two examples that I found interesting, still within the United States, right? So within the system that I just happen to know better. And that's to look at the teaching of economics, the formal field of economics, and the field that becomes computer science, okay? So they both go through a kind of into what we might call an instrumental mode. And again, that's not to say it's unimportant or interesting. It's just it's a particular kind of methodology that rises, becomes ascendant in both of those areas. In economics, again, even in the United States, through the 30s into the 50s, one can find kind of textbooks written by prominent economists that were praised in the scientific literature that were closer to history monographs than present-day economics books. They talked about kind of world systems. They talked about multiple forms of governance, let alone economics, right? Which in the US is amazing to go back and see. It was possible to have that discussion once. And they flourished in a kind of qualitative interpretive mode. There were things that we might now recognize as economic history with quantitative things and trends, but it was a lot of pages of, again, a kind of philosophical analysis of political economy, as well as analyzing essentially supply and demand and things. Okay, it was a mixture. And then, at least in correlation, I won't say it's causation, I don't know the field well enough, but at least in strict correlation, start looking at the increase in student numbers. It's the same story. Look at the types of techniques that get bumped up in value and represented in the next generation textbooks, and more the prizes to which kind of economists, at MIT in particular, but not only there. And you see this very stark shift. Now, again, I don't know enough to fill in beyond the correlation, but I found that striking. Likewise, very quickly in computer science, which is a much newer field to be recognized and called as such, before the enrollments really exploded at MIT, more than half of our undergraduates are majoring in computer science. I mean, they've taken over. Before that era, this was a very small field, often not its own department, either computer science with mathematics, computer science with an engineering field, and so on. And again, they were often in the problem sets I've been able to find in the early textbooks, what we might code as kind of philosophical foundations in a kind of Marvin Minsky mode. Could computers in principle think? What would it be like to have something that they once would have called artificial intelligence, quite different from the kind of generative AI models today? Those were in textbooks, as far as I could find, in limited sample in kind of homework assignments, as well as learning to code, right? Learning different kind of programming languages. And today, right, that it doesn't look like that. It's correlated with growth. With those, I want to be careful and say, there are at least those. So, and I don't know enough about experimental physics or chemistry. I'd love to learn more. But those are some examples that I found very telling.
Okay, as we are already running late, I would suggest that we have an ongoing discussion while we have drinks outside, and we have to leave this room. And please take all your belongings with you, because we have to change the room chairs, etc., for another event tomorrow. Okay, but we can just proceed to the buffet and enjoy another discussion. So thanks again, David Kaiser. Thank you.